Welcome to rational functions. Today's objectives are to graph rational functions and to transform rational functions by changing their parameters. First, I want us to get familiar with the form of a rational function, and a rational function will follow this form. It'll be some function f of x. You'll have a over x minus h plus k. Now let's talk about what all of these variables mean. So A stands for any type of vertical stretching or compressing. H stands for any horizontal translations. And K stands for any vertical translations. So this is similar to other functions that we've worked with in the past. H and K, you know that H will always stand for a horizontal and K will stand for a vertical. Now, rational functions do have a parent function. And the parent functions of rational functions is f of x equals 1 over x. This is the parent function of rational functions. The graph of a parent function is known as a hyperbola. Now we're going to be graphing different hyperbolas, and we're going to be looking at some of the characteristics of what these graphs look like. So let's talk about transforming rational functions. We're going to use the function f of x equals 1 over x as a guide and describe the transformation and graph each function. So right here in this graph below, I have this function graphed out. So if you were to throw in x values into that function, this is what it would look like. Now I want to talk about the characteristics of this and give it names so we know what we're going to be referring to. So we call these parts of the function, of a rational function, branches. So there's one branch here and the other branch is here to the left. Now if you notice, this branch kind of comes down, curves, and almost touches the line y equals 0, but it never actually touches. And the reason that is because there are these kind of barriers here that go across this way, and they happen vertically as well. These are called asymptotes. Now, asymptotes are lines where the function approaches but never touches. So we'll be working with asymptotes a lot in this chapter. So it's helpful to know that asymptotes are lines where the function approaches but never touches. So now let's look at our g of x function. So I have this function that's 1 over x minus 3. If I look at my guide of 1 over x, the only difference is this minus 3. Well, I know from the function that I was given before of x minus h plus k that negative h in this example is negative 3, So h equals 3. So my function is going to be moving 3 units to the right. So by looking at this function, we're able to tell that it's going to be moving 3 units to the right because h equals 3. So now let's actually make some graphs and show what this is going to look like. So we're going to use f of x equals 1 over x as our guide and describe the transformations and then graph each function. So in example A, we have a plus 4 here. So this means our h is going to be negative 4. So this means every single point moves 4 units to the left. So what I'll do is I'll just take, for example, this point here, move it over 1, 2, 3, 4. Take this point here, move it over 1, 2, 3, 4. And then I'll work with this point here. Move it over 1, 2, 3, 4. So one of my branches is going to be shifted over this way. Same thing goes over here. I'll take one of these points, move it over 4 units. 1, 2, 3, 4. Take this point, move it over 4 units. 1, 2, 3, 4. And you could already see this function is going to be dipping down like this. So our asymptotes are going to move over 4 units as well. Originally, they were this line that goes right through here and through here. But now those moved over 4 units. So now those asymptotes are right here. So what I'm looking for is the red lines. Those are the graphs. Let's look at example B. In example B, the difference is now we have a plus 1. So k equals 1, which means my function is moving up 1 unit. So I can just grab some easy points. For example, this point here, move it up 1. This point here, move it up 1. And I know my function is going to look something like this. I can take this point, move it up 1, and this point, move it up 1 as well. And my function has moved up 1 unit. So the biggest part here is to be able to identify what are the changes in the functions. And remember, these original black lines that I showed you, that's the f of x equals 1 over x. These here are just changes to that. Now that we have an idea of what's happening with the shifts, we can look at any hyperbola and identify the asymptotes, the domain, and the range of the function. So in the function g of x equals 1 over x plus 2 plus 4, we know that there's going to be 2 shifts. We know since h equals negative 2, this function moved over 2 units to the left. And since k equals 4, we know this function moved 4 units up. Now, they shifted over 2 units to the left and 4 units up. So their asymptotes also shifted. It's important to know what the asymptotes are originally. In the function 1 over x, the asymptotes were x equaled 0, it was just a straight line through x equals 0, and y equaled 0. So now if there's a shift in the function, there's also a shift in the asymptotes. So if we look at our graph here, let's talk about the vertical asymptote. It goes right through x equals -2. So for the vertical asymptote, we know that x has to equal -2. How about the horizontal asymptote? Because we do need to talk about both of them. When we talk about asymptotes, we always talk about the vertical and the horizontal. So you can see here, and this is kind of a rough estimate, I draw my asymptote through here, and I can see that it's about, because of the graph, it's about y equals 4. Once again, the asymptotes are lines where the function approaches but does not touch. So we identified the asymptotes for the vertical and for the horizontal. Now let's talk about the domain and range. We remember that domain means all possible x values, sometimes known as inputs. So here let's think about which values of x wouldn't work. Now you can always just look at your asymptotes. Think about it. If x equaled -2, what would happen? Well, if I put in x equals -2, I'd have 1 over -2 plus 2 plus 4. That would give me 1 over 0 plus 4. And we know that you can't divide by 0, so this would be undefined. So the domain for this function is all real numbers, but x cannot equal -2. So, interestingly enough, the domain is just the vertical asymptote. Same thing happens for the range. Range is all the possible y values. So let's think about it. Because of the vertical asymptote, we saw that x could not equal -2. For the range, just look at the horizontal asymptote. So y cannot equal 4. So it's all real numbers, but y can't equal 4. Let's identify the asymptotes, domain, and range of the following function. So, I know that the asymptotes, I'm going to get them from my horizontal shift. So, here, my horizontal shift is h equals 3. And my vertical shift is k equals -5. So my vertical asymptote is going to be x equals 3. My horizontal asymptote is going to be y equals -5. Now for my domain, without even graphing it, I know it's going to be all real numbers, but x cannot equal 3. For my range, I know it's going to be all real numbers, but y cannot equal -5. So start to see the connections. If you know the horizontal shift, you know the vertical asymptote. If you know the vertical asymptote, you know the domain. If you know the vertical shift, you know the horizontal asymptote. And if you know the horizontal asymptote, then you know the range. Now, if we're given a rational function in the form of f of x equals p of x over q of x, we should know what this means. So what this means is we're going to have some function that equals function A over function B. Now, function A and B, if it's a rational function, these need to be polynomial functions. So polynomials means it has to have multiple variables. So an example would be f of x is saying we're having a function that equals this function x squared minus 2x minus 3 over x minus 2. So this is a rational function because we have a polynomial on the top and a polynomial at the bottom. If a rational function is written in this form, it helps us find a few things. We are able to find zeros, and we're also able to find vertical asymptotes. To find the zeros, all we have to do is take the top function, so we'll call it function A. We have to take function A and equal it to 0. So for example here, we would do x squared minus 2x minus 3 equals 0. And we'd solve for that. Now to find the vertical asymptote, we just take the bottom function, here we called it function B, and equal that to 0. So here we do x minus 2 equals 0, and we'd solve for that. Now we're going to do this problem, but I wanted to show you the theory first before we apply it. So now let's find the zeros and the vertical asymptotes of the function x squared minus 2x minus 3. So let's find the zeros first. So to find the zeros, I have to take this top function and equal it to 0. So I have x squared minus 2x minus 3 equals 0. I have to factor this to solve this, so I know I need x's here and here. I need a 3 and a 1. My 3 needs to be negative, my 1 needs to be positive. So my two zeros are x equals 3 and x equals negative 1. Now I have to find my vertical asymptote. Which I do by making my denominator 0. So x minus 2 equals 0. So my vertical asymptote is x equals 2. So graphically, what does this mean? Well, we're going to draw a rough sketch of what this function looks like. Now here we have a vertical asymptote at x equals 2. So here's 2, so that means we have a straight line through here. Remember, an asymptote is the line where the function approaches but doesn't touch. Then we have zeros at x equals 3 and at x equals -1. Now, with the information that we're given here and without using a calculator, this is all that we know. Now, by using a calculator and plugging in x values into here, we'd see that our function looks something like this. Here's one of the branches, and another one of the branches starts out here and then kind of dips down over here. All I'm expecting you to do from this is to be able to find the zeros and the vertical asymptotes. We'll talk more about how to figure out all these points in the future. There are some rational functions that do have a horizontal asymptote. Now, finding the horizontal asymptote takes a little bit more investigation. So we have to talk about the different scenarios where there are and where there are not horizontal asymptotes. So if we have some rational function with two polynomials, the horizontal asymptotes depends on the degree. Now we know the degree of a polynomial is the highest exponent value. So we're looking at the exponent values to help us determine if or if there is not a horizontal asymptote. So if the degree of the top polynomial is greater than the bottom, there's no asymptote. If the degree of the top is less than the bottom, the horizontal asymptote is the line y equals 0. Now, if they're equal, the horizontal asymptote is the line y equals, and it's the leading coefficient of p over the leading coefficient of q. So let's call this scenario A, scenario B, and scenario C. And let's look at 3 examples of this now. So for scenario A, the degree of p is greater than q. So for example, if I had f of x equals x to the 4th plus 4 over x squared minus 1, the degree of p, which is 4, is greater than the degree of q, which is 2. So for this one, there's no horizontal asymptote. Now let's look at scenario B. So in scenario B, let's say I had x to the 3rd minus 1 over x to the 5th plus 7x minus 1. Now in this one, p is less than q. So the horizontal asymptote is the line y equals 0. Now for scenario C, let's say the degrees are equal. So I have f of x equals x to the 4th plus 2x over x to the 4th minus x. Now these degrees are equal, so the asymptote is y equals the leading coefficient of p and the leading coefficient of q. Now both the leading coefficients are 1, so it's 1 over 1, or y equals 1. So to find the horizontal asymptote, you have to look at the degrees of the polynomial functions. Now let's identify the zeros and asymptotes of the following functions. So first, let's find the zeros. Now to find the zeros, I know that I take the numerator and equal it to 0. So I have x squared plus x minus 6 equals 0. I have to factor this. So I have my x's, and I need a 3 and a 2. My 3 should be positive, and my 2 should be negative. So my x values are x equals negative 3 and x equals 2. Next, let's find the vertical asymptote. For the vertical asymptote, I know I take my denominator and equal to 0. Here it's easy. No algebra involved. X just equals 0. Lastly, let's find the horizontal asymptote. Now for the horizontal asymptote, I have to look at the degrees. So the degree of the top function, p, is 2, and the degree of the bottom function is 1. Now since p is greater than q, there is no horizontal asymptote. Let's look at part C. So to find the zeros, we look at our numerator. So we have 2x squared minus 2 equals 0. So I'll do my algebra, and I'll have 2x squared equals 2. Divide both sides by 2, and I'll have x squared equals 1. Take the square root of both sides. X equals plus or minus 1. For the vertical asymptote, I have my denominator of x squared minus 4. I equal that to 0. Add 4 to both sides. Take the square root of both sides. And I have x equals plus or minus 2. So here there are two vertical asymptotes. Now let's look at the horizontal. So the degree of the top function p is 2, and the degree of the bottom function is 2 as well. So if the degrees are the same, you have to look at the leading coefficients. Now, the leading coefficient for the top function is 2, and the leading coefficient for the bottom function is 1. Therefore, your horizontal asymptote is y equals 2. And that'll be the end of our video for today. Thank you. Take care.